Section 30.3, the Bohr model of the hydrogen atom. So we've been building up to this model of what is the atom like inside. And so a scientist by the name of Bohr came up with this model, and it turns out it works really well for the hydrogen atom. And it breaks down once you have more than one electron around the nucleus, because it doesn't account for electron shielding effects, the fact that the electrons are repelling each other. But it works really well, again, for a hydrogen atom, because that just has a single electron, or for other atoms that just have one electron. And it's a great basis for then expanding our knowledge of the atom. So what is the Bohr model? The Bohr model says that we have an electron that is orbiting, that's traveling in a circle like the Earth around the nucleus. And there are different energy levels that that electron can orbit at. It can orbit closer to the nucleus or further from the nucleus. Well, when the electron moves from a higher energy to a lower energy state, that extra energy has to go somewhere. And so it's given off in terms of a photon, in terms of light. And so you can look at the energy difference between the initial state and the final state, and that's going to be equal to HF. That describes the energy of the light, that photon there, which you could also calculate, remember, as hc divided by lambda in terms of the wavelength of the light. That just tells you that the difference in energy levels will tell you exactly what wavelength of light is going to be given off in that photon. So you can imagine then, depending on the energy levels, you'll get a different wavelength of light. So how do we get to this equation, and how does it relate to the line spectra? Well, there's a little bit of derivation to get there. So buckle up. Let's see how this goes. So first, we want to look at the energies and the radii of the Bohr orbits. So the energy is going to be a combination of kinetic and potential energy. Kinetic energies are a classic 1/2 mv squared. The electric potential energy, remember, is equal to Q times V, where V is the potential difference. Well, Q here is the electron, so that part's the negative E. So that part makes sense. But how do we describe the potential that's created by this positive nucleus? Well, that's going to be related to the charge of the electron, but it's going to depend on how many protons are in the nucleus, how much positive charge is in the nucleus. So Z is going to be the number of protons. Sorry, I'm not very good at writing, but we're getting that out. And then each proton has positive E charge. So the net charge is plus ZE for the nucleus. And so if we look at the potential created by that, we previously have seen that the electric potential can be calculated with KQ over R. V is equal to K times however much charge there is at the middle, divided by R. So here we're going to plug in our constant K times the amount of charge, Z times the charge of a proton, and then divided by R, which the charge of the proton is the same as the electron, just equal and opposite. So when we multiply that out, we get this equation for the electric potential energy, which is shown here. That's a really handy equation, that the electric potential energy in magnitude is constant K times Z, the number of protons, times the fundamental charge squared, divided by R, the radius of the orbit. Right, and if we add that to the kinetic energy, you can show, and I'm going to skip over the details of here. There are some additional steps that are not shown. They're in the textbook, or I'm happy to talk about them more if you're interested. But the total energy comes out to this negative kz e squared over 2r. And it's negative because the electric potential energy is greater than the kinetic energy of the electron. And that's why the electron is bound to that nucleus. That's why it's trapped there, because of that negative energy. Right. So An assumption that Bohr made, and he just kind of made this assumption and hoped it would work, is that angular momentum is quantized, that it can only have certain discrete values. So that's what's shown here, that angular momentum L is calculated with m times v times r, and that it has to have these integer values of h divided by 2 pi. Why does it have to have just those values? Bohr didn't really know, except that it seemed to work. So with those assumptions, you can solve for the radius and get that the radius, along with the energy equation, is equal to Planck's constant squared divided by 4 pi squared divided by m divided by k divided by e squared times n squared over z. That's a lot of constants out in front, so you can calculate those and get that the radii for Bohr orbits is just going to be 5.29 times 10 to the negative 11 meters times n squared, which tells you what energy level you're on, divided by z. So for hydrogen, z is equal to 1, and then you can just plug in whichever n value you're at. If you're at n equals 1, the ground state, n equals 2, or n equals 3, that will tell you how large your radius is. So that's pretty nifty. Now, even better than the radius is once we know that radius equation, we can get the energy levels. So the energy levels of each of these different radii is given by, again, this giant constant in front with a negative times z squared divided by n squared. The giant constant in front can be calculated in terms of joules per unit. It's 2.18 times 10 to the negative 18 joules. More frequently than not, though, even though I love joules, at the atomic scale, we more often work in terms of electron volts. So we use this lower equation much more frequently, that the energy level of any of these, n equals 1, 2, or 3, or beyond, is just negative 13.6 electron volts times z squared divided by n squared. So we notice as n gets bigger, our number becomes less and less negative. So it gets closer and closer to 0. Right, so if we imagine the transitions between two of these, like between n equals 2 to n equals 1, you could set up energy level diagrams, and that's exactly what's shown here. So we have at n equals 1, for hydrogen, it's the ground state, z is equal to 1, n is equal to 1, so the energy is just negative 13.6 electron volts. If we instead plug in n equals 2, then it's 1 over 2 squared of 13.6, which comes out to negative 3.4 electron volts. If we go to n equals 3, which is another excited state, that's negative 1.51 electron volts. And as n gets bigger and bigger, our energy approaches 0. It goes from being really negative to getting larger and larger until it's at 0. At n is equal to infinity, the electron is removed from the atom. It's just not part of the picture anymore. And so we call anything above n equals 1 an excited state, where n equals 1 is the ground state, that's sort of the default energy level. But if we give it a little more energy, it could get to an excited state. From an excited state, it can fall into the ground state and give off that light. But let's focus in on the electron being removed from the atom, because that's an interesting thing to consider. So we can look at an example with the ionization energy of lithium 2+. So lithium 2+ is a lithium atom, Z is equal to 3. I don't expect you to have that memorized. This isn't a chemistry class, so the problems would tell you that Z equals 3 typically. Lithium atom with only 1 electron, that's what the 2+ means. Obtain the ionization energy of Li2+ in electron volts. So we want to consider here the ground state, and we want to take something from the ground state to basically out of there to get kicked out of the atom. So we can look at the energy levels of what is the difference in energy between the ground state and an energy of 0 when we know it's removed. Well, the ground state we can calculate for lithium, which is a bit different than that of hydrogen, because lithium has Z equals 3, n is still equal to 1 for the ground state. So it comes out to negative 122 electron volts. That's a lot deeper than just negative 13.6. And this, it has to go from this level, negative 122, all the way up to an energy level of 0 in order to be ionized. So the amount of energy that we have to put in to get from negative 122 to 0 is positive 122 electron volts. And that will give us the needed difference in energy to kick that electron out of there, to ionize it. All right. Now, one more thing. If we look at the energy levels for hydrogen, and we look at the different possible transitions, now we understand, if we go back to like the Lyman and the Bohr series is anytime we have an energy transition from something above n equals 2 down to the n equals 2 level. So n equals 2 is our final case, and then it can start at some other initial level from infinity to 5, 4, 3, anything greater than 2. And so Bohr, in his theory, came up with this equation that 1 over the wavelength is equal to a whole bunch of constants times z squared times the quantity of 1 over n final squared minus 1 over n initial squared, where n initial and n final are both just integers, but n initial must be greater than n final. You have to start at a higher energy level and then fall to something lower in order to give off a certain wavelength of light. So Bohr came up with this equation, and the really remarkable thing is that it matches the Rydberg constant that we previously got with the line spectra. So this huge giant mess of constants out in front, it turns out is exactly the same as the Rydberg constant, 1.097 times 10 to the positive 7 inverse meters. And the resulting wavelengths that were observed matched what was predicted, for hydrogen at least, which isn't shown here. So this gives you the most thorough way to calculate the line spectra of the hydrogen atom, that it isn't just any number here, but this is sort of the final state, NF minus an initial. So I encourage you to use this equation when you're doing calculations, but you can just use the Rydberg constant. You don't need to plug in this whole mess of constants. So that was perhaps the greatest accomplishment of Bohr's theory. And so Bohr's theory is still used today when studying the hydrogen atom. The one kind of weird thing with Bohr's theory was this whole angular momentum is quantized. And so 10 years later, a whole decade later, if you can even imagine that, the scientist de Broglie, remember talking about de Broglie, the wavelength of particles, came up with an explanation of Bohr's assumption about angular momentum. De Broglie said, hey, the electron is behaving like a standing wave. If it's a standing wave, then it needs to be an integer number of wavelengths to make it around that circumference in order to fit properly, right? So the electron has some wavelength, and for it to be totally stable and have a standing wave, that wavelength needs to be within the circumference, total distance around 2 pi r. So this is a bit of an aside, but it was a very nifty explanation for why the assumption that angular momentum is quantized actually does make sense. So thank you, de Broglie, for explaining that mystery. So that brings us through sections 30.3 and 30.4.